Okay, hi everybody. So how do Grosvenor bases help find solutions to polynomial equations? So in general, they don't. But if let's call, let I equal the ideal generated by the G1 through GS, and let this be a Grosvenor basis for I. But if the variety of I is finite, namely it's a finite number of points, so let's say there are polynomials in 3 variables and the variety was like, these 5 points, then what happens? Then a lexicographic Grosvenor basis will help. Well, what does help mean? Help means that a Lex Grosvenor basis will, and then I'll use the word triangularize your equations. In particular, there will be an equation with only one variable, among the Grosvenor basis elements, the GI from a Grosvenor basis. Okay, so in general they don't, but if the variety is finite, then a Lex Grosvenor basis will help. A Lex Grosvenor basis will triangularize your equations. In particular, there will be an equation with only one variable among the GI. That equation could be solved by methods pertaining, methods that treat polynomials in one variable. Polynomials in one variable. And those finitely many solutions can be plugged into another of the GI or the GJ, which is guaranteed to have only 2 variables. And let's call that one variable xn, the last variable, and then some other polynomial will have xn minus 1 and xn, in which case you can plug in for xn and again get a univariate polynomial, etc., with each stage requiring solutions of univariate polynomials. This means one variable. Univariate is one variable. Like unit is one. Okay. So yeah, now how does this work? Why does a lexicographic Grosvenor basis do this? Well, the answer is in section 3.1, and it is right here, involving the elimination ideal, and in fact the elimination theorem. So if we order the variables like this, then we just take the lexicographic Grosvenor basis, and we only look at the polynomials that have these variables, and that will be a new smaller set, a subset of G, G is just a set with finitely many elements, just these generators of the polynomial ideal. And GL will generate the elimination ideal. And yeah, so really we need to read section 3.1 and also 3.2 to really understand the implications of this theorem. But if we take our Grosvenor basis and we just look at the polynomials in the last variable, then this will be, I guess, one polynomial. And that's the polynomial we solve. It's in one variable. So really, this question is sort of begging future questions about sections 3.1 and 3.2. Okay? But what was my answer? I just described what will happen. I didn't describe why this happens, but only that it does happen. Yeah, so this is the answer, but not the reason that the answer will always work. For example, this didn't say prove that the elimination ideal, blah, 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 blah.